Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com.
Hello, everyone.
I am your guide for today, and we are going to crack open a topic from Class 12 Physics, Unit 6, Electromagnetic Induction.
Okay, I have looked at the schedule, and today is the experiments of Faraday and Henry.
That's right.
And I have to be honest with you, I almost skipped the session.
Skipped it. Why is that?
Well, it just feels a bit like, I don't know, ancient history. I mean, we have quantum mechanics and all this high-tech stuff. Why are we spending so much time on guys playing with magnets back in 1830? I usually just, memorize the formulas and move on.
And that is exactly where students lose marks in the conceptual sections. You see, the formulas are easy. Anyone can memorize E equals minus d phi by dt.
Right.
But these experiments, they are the closest thing to magic in our entire syllabus. If you don't get the story behind the formula, the trickier exam questions will completely stump you.
Magic. That's a strong word for a physics class.
I mean it. Today, we're going to break these experiments down so simply that you won't just memorize them. You will actually see the world a bit differently. Exactly what answer it requires, but in a way that sticks.
Okay, you have my attention. Prove the magic part.
All right, let's start with a little challenge. Picture this for me. You have a small light bulb, maybe an LED.
Okay, a bulb.
And you have a coil of copper wire.
Yeah.
Just a simple loop of water.
Bulb and wire. Got it.
Now, here are the rules. You have no battery, no cell, no plug point, no solar panel. Nothing that we normally call a power source. Can you make that bulb glow?
Without a battery, that sounds impossible.
Why?
Well, physics 101, right? You need a potential difference to drive a current. You need a source. If I just have a wire and a bulb, it's just metal and glass. It's dead.
That's what common sense says. And it's what everyone believed for centuries. But here is the wait, what? Moment. It is possible. You can generate electricity just by moving a piece of stone, a magnet near that wire.
Just moving it.
Just moving it. And it gets even weirder. You can make electricity flow in your wire by just clicking a switch in a completely different wire kept nearby.
No, wait.
No touching, no physical connection at all.
That sounds like a ghost story or something. You're saying I can push electrons around in a wire without actually hooking them up to a battery?
Exactly. That ghost is what we call electromagnetic induction. And it was discovered by Michael Faraday and Joseph Henry around 1830. Before them, people thought electricity and magnetism were two different subjects.
Like two different chapters in a book.
Exactly. A chapter for electricity, a chapter for magnetism, and they never, talk to each other. These experiments prove they're actually two sides of the same coin.
Okay, so the moving magnet replaces the battery, but how? What's the core idea here?
This is the thing you need to lock into your brain. The experiments proved that when the magnetic environment of a conductor changes, a current is produced.
So the key word is change.
The key word is purely and only change. You don't need a battery, you need a change. Let's try an analogy. I want you to imagine a cricket stadium.
Okay, fine. I'm picturing Wankhede Stadium. It's a packed crowd.
Perfect. That
Yeah.
crowd. Those are the free electrons inside your copper wire. Now, imagine the magnetic field is the excitement level of the match.
Okay. Magnetic field equals excitement. I'm with you.
Now, imagine it's a really boring test match. The batsmen are just blocking every single ball. The excitement level is there. It's a match, but it's steady. It's boring. What's the crowd doing?
They're just sitting there, probably checking their phones. Nobody is moving.
Exactly. Steady excitement means the crowd sits still. In physics terms, a steady magnetic field means zero current. The electrons are just sitting there.
Makes sense so far.
But now, boom, a
Yeah.
wicket falls. Or, Kohli hits a six. The excitement level changes drastically in a split second. What happens to the crowd now?
Oh, everyone jumps up. They're waving their arms, shouting. They move.
They move. And once the replay is over and the game settles down again, they sit back down. They stop moving.
So they only move during that moment of change.
Yes. And that is exactly how electrons behave here. They're lazy. They only move, creating a current when the magnetic environment around them changes.
Wow.
Even if the magnetic field is super, super strong, if it's constant, the electrons just sit there like a bored crowd.
That's a really helpful way to think about it, because I always thought a strong magnet must mean a strong current.
I mean, that's the trap.
But you're saying a strong magnet just sitting there does nothing.
Absolutely nothing. We can actually visualize this. Let's build a mental image. Close your eyes for a second.
Okay, eyes closed.
Visualize a coil of copper wire. Your stadium? Now connect its ends to a galvanometer. You remember what that is?
Yeah, the little box with the needle that moves left or right when current flows.
Right. Now picture a bar magnet held right in front of that coil, perfectly still. What's the needle on the galvanometer doing?
Based on the cricket analogy, it's doing nothing. It's at zero.
Dead at zero. It could be the strongest magnet on Earth, doesn't matter. But now, in your mind, grab that magnet and push it towards a coil.
Okay, pushing it in.
As you push it, the needle jerks to the right. It deflects.
And if I stop moving, even if the magnet is inside the coil?
The moment your hand stops, the needle snaps right back to zero.
That is so counterintuitive. You'd think if the magnet is inside, the power is inside.
But the power isn't in the magnet itself, it's in the motion. The universe is basically saying you can't get energy for free. If you want electrical energy, you have to do mechanical work by moving something.
No free lunch in the universe.
Exactly. So now that you have the intuition, let's look at the official textbook language because we need to write precise answers for the exam. Can you open the source material to experiment 6.1?
Got it right here. Experiment 6.1.
Could you read the description for us?
Okay, insert says, when the north pole of a bar magnet is pushed towards the coil, the pointer in the galvanometer deflects, indicating the presence of electric current in the coil. The deflection lasts as long as the bar magnet is in motion.
See? As long as the bar magnet is in motion, that's the key. Okay, so let's unpack the three main observations here. First, pushing the magnet in causes a deflection, say, to the right.
Right.
Okay, second observation. What happens if you then pull the magnet OT?
Let me just check. It says, when the magnet is pulled away from the coil, the galvanometer shows deflection in the opposite direction.
So push in gives a deflection to the right. Pull out gives one to the left. The direction of change matters.
Okay, so in is positive, out is negative, something like that.
Exactly. And the third point, which is crucial for numericals later, what if you move the magnet really, really fast?
The book says, the deflection is found to be larger when the magnet is pushed towards or pulled away from the coil faster.
Speed matters. Faster change equals more current. Simple.
Okay, experiment 6.1 is clear. But you mentioned something about clicking a switch earlier. That sounded more interesting than moving magnets.
Yes. That leads us to the next experiments. You see, scientists ask, do we have to use a magnet? Can't we use another current to do the same job?
Oh, because a current-carrying wire also creates a magnetic field, or Stead's experiment.
You remember, yes. So in experiment 6.2, they just replaced the bar magnet with a second coil, let's call it C2, and ran a current through it. It became an electromagnet.
So now I have an electromagnet and my original coil.
And if you move this electromagnet towards the first coil, C1, what do you think happens?
Well, it's acting just like a magnet, so moving it should do the exact same thing. A galvanometer and C1 should deflect.
Bang on. It's exactly the same. But moving coils around is a bit clumsy. This leads to the real climax. Experiment 6.3. The case of the stationary coils.
Stationary, so nothing moves at all.
Nothing mechanical moves. Imagine two coils, C1 and C2, just sitting side by side on a table, glued down. C1 is connected to the galvanometer.
And C2 is connected to a battery.
Yes, but, and this is the key, through a tapping key, the switch.
Okay, I have my finger on the switch. It's open.
Right. So no current C2, no magnetic field.
Right.
Galvanometer in C1 shows
0.
Now, press the key.
Click, current starts flowing in C2.
Now think in slow motion. Does the current in C2 go from 0 to, say, 10 amperes instantly?
No, I guess. It would take a tiny fraction of a second to rise to its full value.
Exactly. And in that tiny split second, the current is changing. And because the current is changing, its magnetic field is growing.
It's expanding outwards. And because that field is changing.
Oh, the galvanometer in the other coil should move?
Yes, it flicks just for that split second. So now what happens if you just keep holding the key down? The current in C2 is steady at 10 amperes.
Well, if the current is steady, its magnetic field is steady.
And if the field is steady, what does our cricket crowd do?
They sit down, the current in C1 stops, the needle goes to 0. Exactly. This is what confused so many scientists. You have a massive current flowing right next to coil C1, a huge magnetic field, but the galvanometer reads 0 because there's no change.
That is wild. So it only blips for a microsecond when I press the switch.
Yes. And here's the kicker. What happens when you now release the key?
The current drops from 10 amperes to 0. That's also a change, a very fast change.
The field collapses.
So the galvanometer should flick again, but in the opposite direction this time.
You got it. It flicks the other way. You are inducing a current in a totally separate wire just by clicking a switch on and off.
That's basically how a transformer works, isn't it? Or wireless charging.
It is the exact principle. Your phone's wireless charger works on this experiment. One coil in the pad, one coil in the phone. No wires between them, just a changing magnetic field transferring energy.
Okay, now I really see why this is important. It's not just some old experiment. It's literally how my phone stays alive.
Precisely. And I hope this visualization is helping. Just a quick reminder, this concept explainer is from ProfSam.com. That is PROFFAM.com.
Okay, so we've got moving magnets, moving coils, and tapping keys. The speed thing is still a bit fuzzy, though.
Let me give you a really simple example. No complex calculus, just logic.
Okay, go for it.
Imagine pushing a north pole into a coil. It takes you exactly 1 second. And let's say the needle deflects to position +5 on the scale.
Okay, 1 second gives +5.
Now, what if you push it in really, really fast, say in 0.1 seconds?
The change is much faster, so the deflection should be much bigger, maybe +50.
Exactly. The rate of change was 10 times faster, so the induced current is roughly 10 times larger. The induced EMS, what drives the current, depends on how fast you change the flux.
Got it. Speed is king.
Now, we need to talk about the silent killers. These are the common misconceptions that students write in exams thinking they are correct.
Oh, the exam traps. What's the biggest one here?
We've touched on it, but I still see it every year. Misconception number 1. A strong magnetic field creates current.
Yeah, I fell for that at the start. It just feels so intuitive. Big magnet, big power.
You have to fight that intuition. Just remember, no change, no current. You could be standing on the strongest magnet in the universe, and if you and your wire are stationary, your bulb will not glow.
Okay, no change, no current. Got it. What's the second one?
Misconception number 2. Thinking only the magnet can move.
Well, in the diagrams, it's always the magnet that's moving.
True, but that's just for convenience. In physics, only relative motion matters. You can keep the magnet fixed and move the coil towards it. The result is exactly the same.
Or move both of them towards each other.
Yes. As long as the distance between them is changing, current will flow. But what if you move both of them at the same speed in the same direction, so the distance is constant?
Relative to each other, they're not moving, so zero current.
Perfect. You're thinking like a physicist now.
I'm getting there, but I'm worried that in the exam hall, under pressure, I might forget all this. Do you have a memory hack or something?
I do. A phrase and a physical gesture.
Okay, let's hear the phrase first.
Move or vary to make current carry.
Move or vary to make current carry. I like that.
Move refers to the magnet or the coil. Vary refers to varying the current with the switch. Both actions make the current carry or flow.
Simple enough. What about the gesture?
This is my favorite. In the exam, if you get stuck, I want you to imagine you're holding a round doorknob.
Okay, holding a doorknob.
Yeah, just hold it tight. Don't move your hand at all. Is the door opening? That's your steady flux. Now, twist your wrist back and forth. Open, close. That twisting motion, that is change. That is your d5 phi by dt.
So holding is nothing. Twisting does the work.
Exactly. A steady hand does nothing. You must change the position to get a result. So if you're looking at a question with a stationary magnet, look at your hand. Are you twisting? No. Then the answer is 0.
That's actually really helpful. People might think I'm going crazy twisting my hand in the exam hall, but hey, if I get the marks.
That is all that matters.
Okay.
Okay, let's summarize this into 3 exam safe points.
Ready.
Point 1, relative motion. Current is induced when there is relative motion between a coil and a magnet, or between 2 coils. Point 2, stationary induction. Current is also induced if the magnetic flux changes because of a varying current in a nearby coil, usually with a tapping key.
The transformer principle, check.
And point 3, the speed factor. A faster movement or a faster change in current produces a larger induced current. The magnitude depends on the rate of change.
Rate of change. Perfect. I think I'm actually looking forward to the next chapter on this now.
It makes you wonder, though, if electricity is only created when things change, maybe that's a fundamental rule of the universe.
What do you mean?
Maybe stability is just dead energy, and it's chaos and change that actually power everything.
Oh, that got deep fast.
Something to think about next time you flip a light switch.
Definitely. Thanks so much for explaining all this.
You're welcome. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com. Keep practicing, keep questioning, and we'll see you in the next deep dive.